In this video lecture, we'll cover section 4.4, which covers the derivative rule of the chain rule. And this will continue our exploration of derivative rules for the different functions that we'll work with in this course. So you can go ahead and read this first page on your own, but this kind of summarizes what we've done so far. And we'll start with the definition of this derivative rule. So at this point, it's very important that you're comfortable with the previous derivative rules that we've discussed, in particular the power rule, but also the product rule and the quotient rule. So if you're not familiar with those, I would definitely recommend that you pause this video and get some more practice with those before going on. And that's because we'll be using combinations of these derivative rules as we go. So this rule is defined in the green box here, and it tells us how to take derivatives of compositions of functions. So the main idea, the main application that we'll use this for is that we'll have some sort of function, let's call it h, and we'll be able to view that function as a composition of two more elementary functions. And the idea is that we may not know how to calculate the derivative of this function h on its own, but if we can view it as a composition of functions, this rule tells us how to find such a derivative. So to give you an example, we could have something like this. So using the rules that we previously discussed, we have no good way to differentiate this function. This is the quantity x squared plus 1 raised to the 100th power. So we could use product rule many times, but that would be extremely tedious. And furthermore, what would happen if we wanted to differentiate something like now the quantity x squared plus 1 raised to the 1000th power, and so on. So we need a better strategy, and that's what this rule allows us to do. So the idea is that we can view this function as a composition of two elementary functions that we do know derivatives of. And those two compositions, or those two functions, would be the function x squared plus 1. We know how to handle the derivative of that. And this outer piece that's in blue, we could think of that as a function x to the 1000, such that when we compose these two functions, we get the quantity x squared plus 1 raised to the 1000th power. So we're going to go through several examples, and it takes quite a bit of practice to be able to visualize functions in this way, but with enough practice, anybody can do it. So let's walk through how to do this, and this example has been provided for us. And so let's work through this example on our own, and this detailed solution is provided for you to reference should you need to later. So let's rewrite this function. So when you're looking to take the derivative of any function, you should sort through a decision tree in your mind, working from the most elementary rules up to this rule, the chain rule. And there are many ways to approach this, but I find that's the quickest and most consistent way to solve these derivatives. The first thing we can notice is that we have this term x squared plus 3, and we know how to take that derivative just using the rules covered in section 4.1. However, this is wrapped up in this function x to the 5th, or something to the 5th. And so this is not multiplication, this is not division, so quotient rule and product rule won't help us here. So by process of elimination, we may want to consider if chain rule can help us. And chain rule is the rule that we're working on today. What does chain rule look like? We just looked at it in the green box above. It says that if h can be written as a composition of two functions f and g, then the derivative is given by the following. The derivative of the outer function f composed with the inner function g times the derivative of g. So remember that this notation is composition, not multiplication. So when we see this term f prime of g, this is not f prime times g, this is f prime composed with g, and that is to say the output of g is fed into f prime. So we'll bear that in mind as we work with this, but the first thing we need to do is envision h as a composition of two functions f and g, and we will choose those functions, and we want to make a choice such that the two functions f and g compose to give us our function, and our functions such that the derivative of f and g can be found using our other rules. So basically the rules from section 4.1 in most cases. So one tip is to use parentheses to help. So in a function like this, the term x squared plus 3 is inside the parentheses, and what's left over is something to the 5th power. So if we called the term in the parentheses our inner function, g, then our outer function would be what's left over. So in this case, we would call that f. And f and g are just labels for functions. And we're just trying to write h in this form so then we can use that derivative definition of the chain rule. So we let f be what's left over, and an easy way to do that is to kind of cover up what you've accounted for. So we've already accounted for x squared plus 3, and just put an x in there, and that gives you your outer function. We can always do a sanity check and ensure that h equals f of g. That's what we're trying to do first. So we can test this by composing f with g. So remember, composition means you stuff one function inside of the other. So we'll do a check. So if we substitute our choice for g into f, we get the following. And then what does f do to its input? It raises it to the 5th power. So in the end, this composition gives us the quantity x squared plus 3 raised to the 5th. So this checks out. Our choices work such that the composition of f with g gives us our function h. So that's the idea, is that the choices that we made make sense in this context. So from here we can simply use the provided definition of the derivative of h and solve our derivative. So you can think of this line, this definition of the derivative. This is the chain rule. You can think of this as our instruction for how to find the derivative. So if you look at each term on the right hand side, we need f prime, we need g, and we need g prime. We already have g. That was something we defined. So that's this quantity, x squared plus 3. So we need to find f prime and g prime, but we can do that because these are more elementary functions. So we can just write those in the margin for some good bookkeeping. So g prime is 2x, and this is where, as I mentioned before, we really need to have a good grasp on the previous derivative rules, otherwise this will really be a challenge for us. So g prime is 2x when we take that derivative of g, and when we take the derivative of f prime is 5x to the 4th. So now this is just a matter of substitution into our derivative definition. So just a reminder that I think we all agree that f and g are functions, but sometimes there's confusion about the derivatives. Those are also just functions. So we have rules to find derivatives, and derivatives have special relations to the original function, but they're also just functions. So this formula for the definition of the derivative of a composition of functions, call this chain rule. This is just at its most basic a composition of functions and a product. So let's write that out and see what we get. So I like to substitute this in stages. You could substitute it all at once, but let's just do it one step at a time. So we'll substitute g in here. So we've defined g to be the quantity x squared plus 3. And then we can substitute this part, g prime, and that is 2x. So this is a product here. And so now we just need to evaluate f prime at the quantity x squared plus 3. So in other words, we need to plug that into the function. So go over to f prime and look at what the function does. It takes whatever its input is and raises it to the 4th power, then multiplies everything by 5. So to write this down mathematically, we need to raise the input down. We need to raise the input to the 4th power and multiply that by 5. So that's f prime, and what our input is this quantity x squared plus 3. So from there, we just copy down the rest of the expression, and we've found the derivative function. So that example actually covers the chain rule and everything you need to know to apply the chain rule. However, it requires a lot of practice. So the rest of these notes will go through several examples. I would encourage you to pause the video before each solution and try these problems on your own so that you can start to practice. Okay, so again, just working through the decision tree of how to know to use chain rule. We see this function t plus 1 raised to the fourth, that whole quantity, t plus 1. And so we could find the derivative just using rules from section 4.1 of t plus 1, but when we wrap it up and raise it to the fourth power, it's not clear. We could distribute the fourth power and kind of expand that algebraically, but as we discussed at the start, that may not work for higher powers. That may not be practical. So if we had the 100th power here instead, that would be very impractical. So in general, we want to stick to using the rule that makes this quick and efficient. So the product rule doesn't help us here because this isn't a product of functions, neither is it a quotient of functions. So work through that decision tree and convince yourself that we should look at thinking of this as a composition of functions so that we can use chain rule. So the two functions then should be a product of an outer function and an inner function. We've been using f composed with g, but this function is called f. So we can just use a different name, so h composed with g, and we want our variable to match, so that should be t. And so the idea is we want to write f as a composition of these two functions. And we need to find these two functions. So if we define the inner function to be the function inside the parentheses, that leaves an outer function of t to the fourth. So according to our labeling, our g of t will be t plus 1, and our f of t will be what's left over. So again, just cover up what you've already accounted for with your finger, so that highlighted region, and just put the variable in there, and that will give you a method to find your outer function if you have any confusion. So if we do that, we just drop in t, then our outer function is t to the fourth. From here, we can write out the chain rule, and the rule is that f prime is given in terms of h and g, and their derivatives as h prime composed with g times g prime. So that's the chain rule. So as we discussed in the last example, now that we have our f and g and we've written down our derivative rule, then all we need to do is find the derivatives of f and g. And so I see I've made a typo here. So g is okay, but my label here for f is wrong. So this is what I meant to write is h. So this is representing our outer function h. So now that everything looks good, we can go ahead and find our derivatives. And this is also why it's really important to have good bookkeeping. So if you do make a typo, it's easy to go back and find where you went sideways. So just using power rule, we get that the derivative of t to the fourth is 4t cubed. The derivative of g is just 1 for the first term and 0 for the second term. So now that we have those derivatives, we simply substitute those functions into our formula. So this gives us the following, and again I recommend doing this in a couple steps the first few times you do this. So we substitute g of t, which is right here, into our derivative, and so that is just the quantity t plus 1. And then g prime is next, and that's just 1. So that won't change anything, but we can just write times 1 just to be clear about our work. So lastly, we just need to evaluate h prime at the quantity t plus 1. So what is, again, h prime, what does it do to its input? Its input is t, and so it raises t to the third power and multiplies by 4. So to write that down, this is kind of the structure of h prime. And so the input is not t, but t plus 1. So we should put t plus 1 in there. And times 1 doesn't change anything, so this is our final answer. So this is just a short discussion about kind of what not to do. So our intuition often betrays us, and intuitively we might think that the derivative of a composition of two functions f and g is found just by moving that derivative to both f and g, and so that's simply not true. And so you can look at this example here. It's similar to examples we've done, and you can apply chain rule to get that derivative, and you can apply this kind of pseudo rule, and you'll see that you get different solutions, and you'll see why that is wrong. So go ahead now and practice the chain rule with these problems, and I will provide those solutions. So let's run through this and point out a few details for each of these solutions. So for part A, we've viewed this as a composition of two functions, the function inside the parentheses t cubed plus t. So that will be our inner function, which we're calling g. So you can see that association there. What's left over is something to the 100th power, so that will be our f, our outer function. From here, we just follow that chain rule. So chain rule is given by the third line, and so we'll need f prime and g prime, and we find those there according to the rules covered in section 4.1. So from here, the last step is to simply substitute our functions into the definition of the derivative highlighted in yellow there. So that is done in the last step, and that provides us with our final solution. So you may need to include a sub-step in between those two, and definitely do that as necessary. So that sub-step is included over here. So you can see first we want to make the substitution of g, and so we plug in g, and then we evaluate f prime at t cubed plus t. So that gives us our first term. So this example is very similar to part A. The only maybe new thing or new part of this example is that we have a coefficient out front, but nonetheless we can still use the parentheses to kind of give us a good choice for our inner function. In this case, we're calling it g of r. So we choose g of r to be our inner function, 2r plus 3, and that leaves our outer function to be 5r to the 5th. Again, we write the definition of the chain rule, and so that reminds us that we need f prime and g prime, so we evaluate those using our functions and derivative rules, and from there we make the substitution. The first term, f prime of g, is often challenging, so again we can do that on the side, and so we substitute g, so that means we need f prime of the quantity 2r plus 3. F prime is the function that raises things to the 4th power, then multiplies by 25. So we drop 2r plus 3 into that function, and we have that entire term. The last question looks quite different than the other two, but in fact it is of the same form, and that's because the square root function is just the 1/2 power. So we can write this function as the quantity 1 minus t to the negative 1 raised to the 1/2, and the other property that we're using is another exponent property. So this is helpful for the derivatives, that's why you would want to write it this way. And so again, we can use the parentheses to choose our inner function to be that function inside the parentheses. So that will be our g here. That leaves our outer function to be what's left over, in this case t to the 1/2. So that's our f. Again, we'll now write the definition of the chain rule and proceed to find f prime and g prime. So this is a very procedural process, and by doing many of these, you'll get it figured out. So you can see, again, that first term, f prime of g, is written out on the margin just to make sure we get that term right, and then we make that substitution to finish the problem. So go ahead and try this one on your own now, and I'll provide you with the solution now. So here the solution has been provided without all the supporting structure that we saw in the previous problems. Once you get comfortable enough, you'll be able to evaluate these derivatives in one step. There was a pre-step that I did, which was to write our function in an equivalent form, which was the negative 1 power. So remember, 1 over some quantity is equivalent to that quantity raised to the negative 1 power. So in this case, that allows us to write this in a way that we can successfully apply chain rule. Alternatively, since this function can be viewed as a quotient, you could also apply quotient rule and successfully find the derivative. So either approach that you prefer is fine. Those would be equivalent answers. If you do use the quotient rule, it's likely that your answer will look different. However, you could simplify to show that this is equivalent to the solution provided here. So we saw a problem like this in the previous sections, and so let's go ahead and see how we solve this for compositions of functions. So it will really be the same approach. The only difference to this problem is that h is given as the composition of f and g, and similarly k is given as the composition of g and f. You might have some intuition that these should be the same thing, but that's not necessarily the case. So g composed with f is generally not the same as f composed with g. So if you recall, when we did this problem for product and quotient rule, the first thing that we did was write out the definition of the derivative, considering what they gave us for the function definition. So in this case, h is the composition of f and g. So this means by chain rule, so following this definition, h prime of 2 then is equivalent to f prime of g of negative 2 times g prime of negative 2. So this means we need to first find g of negative 2 and g prime of negative 2. Recall from section 4.3 that the derivative of these piecewise linear functions is just the value of their slope at that x value, because the tangent line would just sit on that line. So the rate of change is constant for any linear function, and it's precisely the slope. So what we calculated last time was that at x equals negative 2, the derivative of g is 1/6. So g prime of negative 2 was 1/6. So check out the 4.3 lecture video to see that derivative calculation, but that's how we did that, is by finding the slope of that red dotted line for g. And g of negative 2, so this is the function values, and g of negative 2 is our function height, is about 2/3. So now we update our definition of the derivative, and so we need f prime of 2/3. So I mentioned at the start of this video that this is a composition, it's not a product. So I see a lot of students trying to multiply some values here, but this is a composition, so that means we should be inputting values into the function f prime. So we find the value of g of negative 2. We found that to be 2/3, and so we make that substitution. This tells us that we need f prime of 2/3. G prime of negative 2 is just 1/6, so we already have that value. So f prime of 2/3 is the slope of the line at x equals 2/3. So going to 2/3 and looking at the blue line, it's the slope of that corresponding line. We already determined that that was negative 1/4 in the previous lecture, so again, check out the video lecture for this problem for section 4.3. So making that substitution gives us the following result, negative 1/4 times 1/6, which gives us negative 1/24. So hopefully you can see that this problem is almost identical to the similar problem in section 4.3. The only real difference is in the way that h and k are defined. So go ahead and try to calculate the next problem on your own following our example above, and I'll provide that solution. So this is what you should come up with. So when we write out the derivative according to chain rule for k of x, we should get the following expression, and that's because, remember, k is the composition of g with f. So this looks a little bit different, and when we substitute x equals negative 2, we get the following equation, and this means that we need f of negative 2 first and f prime of negative 2. How f of negative 2 is function value, and that's not a problem, but if we come back up to the plot, we see that f prime at x equals negative 2 is at a sharp corner, and anywhere you have a sharp corner, the function is not differentiable. So in other words, the derivative does not exist there for f, so there's no way to define the derivative using our limit definition. So just to put it another way, f prime of negative 2 does not exist, And so since that's part of our expression for k prime of 2, that also implies that k prime of negative 2 does not exist. So let's take a look at a word problem. And these look quite different for a chain rule, so definitely make sure you attempt several of these from the textbook so that you're comfortable with chain rule in the context of a word problem. So we're given two functions here. The first one is a percentage y of a total personal consumption that an individual spends on food, and x is the percentage that an individual spends on education. So y depends on x and x depends on t. We're asked at the end to estimate how fast the percentage spent on food is changing at a particular time. So to unpack this, we need to recognize it's asking us to determine how fast something's changing. So this is a derivative, but it's a derivative of y with respect to t because time is November 1st. So this will be, in this case, t equals 10. You may think wait a second, November is the 11th month, but that's because we consider January the first month. But mathematically, we would count January as 0 since time is starting January 1st. So this is the time, November 1st, and we want to know how fast this function y is changing at that time. So the only way to think about y in terms of t is to compose x and y. So what we want is the derivative of y composed with x at t equals 10. So this is a shorthand way to write an expression for the derivative of a function at a point. So the prime notation means we want the derivative or the rate of change, and the subscript is telling us where we want to evaluate that. So this means we're going to need chain rule, and so we can just write that out. And the nice thing about this problem is that the functions are already decomposed, so we don't need to figure out our inner and outer function. We already know what those are from the problem. So this gives us the following. So this shows that we need x and y prime, so we can take those in the margin. So once we have those derivatives, we can simply evaluate our definition of the derivative. And we want to remember to plug in t equals 10, so we can just write that in the subscript as such. So when you simplify all of the scalar factors by multiplication, you end up with a single scalar factor of negative 1.75. From here, the only thing left to do is to evaluate this expression at t equals 10. So the units here will always be the units of the outer function per the units of the variable. So this will be the total percent spent on food per month. This last problem provides another example of chain rule in the context of a word problem. So the key to solve a problem like this is to unpack this thing and all the information contained. So we're told there's this function g which depends on s, and s depends on t, time in hours. So immediately we can see that this can be thought of as a composition g composed with s. So now we can mathematize the given statement. So we're told that 0.05 gallons of gas are consumed for each mile. So that would be telling us that g prime of s for all time is constant, and it's 0.05 gallons per mile. We're also told that the change in position is 30 miles per hour. So that means s prime of t is precisely 30 miles per hour. We want to know how fast gas is being consumed, so this would be gallons per hour, which would be precisely the derivative of g of s of t. So according to chain rule, g of s of t has the derivative g prime of s times s prime of t. However, if we look at what we've unpacked, we have both of those terms. So we can simply substitute those values in, and all we need to do from there is multiply, and we'll have our solution. So g prime of s is 0.05, and s prime is 30. So if we include the units, we can see, to convince ourselves, that the resulting units will give us what we're after, which is how fast the gas is being consumed. So we can see I made a typo here. G prime of s of t should be in gallons per mile. So this gives us a final answer of 1.5 gallons per hour. So the last example walks you through how to take the chain rule of a function 2 times as necessary. So this is an example of a function where we have to apply the chain rule twice to find the derivative. So go ahead and take a look at that, and you can practice some related problems in the suggested homework.